Ice, ice, baby!
Welcome to our second video about electrochemical impedance spectroscopy. I would like to start with a short recap on the current responses of electrical circuit elements, which are essential for the interpretation of the impedance of electrochemical interfaces. If a voltage is applied to an ohmic resistor, a current flows which is proportional to the applied voltage. The relation between the voltage and the current is described by the ohmic resistance R. Whereas for the capacitor, the current flowing is proportional to the rate of change of the applied voltage. This relation is mediated by the capacitance C. In electrochemical experiments, we usually perturbate the system by applying a voltage. This can be done with a step function, or as we would say in electrochemistry, by chronoamperometry. For an applied voltage step, the current response of a resistor 2 is a step function. However, at the moment a voltage step is applied to a capacitor, theoretically an infinite current flows charging the capacitor. In impedance spectroscopy, we often apply an alternating voltage. The resistor again responds proportional with a current response. That means dividing the input voltage by the current response at this time yields the same value as for another point in time. So we need only one parameter, ohmic resistance R, to describe the relation of input and output. When we apply a sinusoidal alternating voltage to a capacitor, the current response is proportional to the first derivative of the voltage applied. We therefore observe a cosine function in response. Simple division of voltage by current at different times gives different results. To describe the response, we must first phase shift the current response and then calculate the quotient. This means we require two parameters to describe the relation between applied perturbation and system response. These two parameters constitute the impedance of the system.
We had considered sinusoidal voltages as applied to an electrochemical system and the corresponding sinusoidal responses that we receive. Let us take a step back and consider other ways of representing sinusoidal voltages that may be easier to work with later on. First, let me again draw a sinusoidal voltage. Again, we have the voltage u over time t. Let us consider this function now in the display of a rotating point in a coordinate system. To make this more concrete, let me draw this coordinate system here. Now, we are trying to project this function with respect to time to a rotating point in this coordinate system, which will then describe the circle as we move through time. Now let us think about how this projection should look like. We begin at time equals 0 at this point, and if we want to transfer this to this y-axis here, it must also be at y equals 0. I will draw this here for now and name this point 1. As we move up here, we are going towards higher y. So we are moving upwards here. And we may reach, for example, here, point 2. And we move over here, we project this here. If we reach the y-axis itself in this diagram, we are at the maximum that this function will ever reach. We are at its amplitude. And this is point number 3. And if we move further and further along the circle, we get towards now falling y values, which is this trajectory. Consider one point here, for example, point number 4, and we put this over here. So this intersects point number 4, and then we move further on, complete the circle. For example, here, as you might recall, we may finish with point number 5 in this region. So at this time point here, 4 is at this point, 3 at this point, 2 here. Now, point number 5 is where the function is reaching its minimum. We are here, point number 5. And eventually, once we have finished one period of the function, we are back where we started. We are at point 1. And so if we move through this function with respect to time and express this in terms of this moving point along the circle, we are moving in this direction, in the mathematically positive direction, along the circle, and we complete one circle for one period. Now, another way of saying that we have completed one circle in one period is to express it as a fraction, which is 360 degrees for a circle in one period, and I will call the period of this function t, capital T, which we have completed here, and we complete 360 degrees in one period t. And what we have done now is essentially relate this kind of display, where the function moves through angles, with the time it takes to move through these angles. We have slightly altered our display in this case, and the ratio between these two we call angular frequency. And I call this omega here, angular frequency. You may recall that from the definition of the sinus function and the unit circle, sometimes the circumference of the circle calculated by 2 pi r, which is 2 pi times 1, if r equals 1 in the unit circle, the 360 degrees is a distance of 2 pi, according to this calculation. And so sometimes you will see this angular frequency when you express the angle that you have here, not in degrees, but in the distance traveled along the radius of the unit circle. You see it written as 2 pi over t. And these are equivalent ways of saying that we have completed one circle in this description in one period. And afterwards, we basically start this entire cycle anew. Now, when we have transformed it like this, we could also plot this function with respect to phase angle. I will call the phase angle for the voltage U, phi with the index U, for coherence sake. Let me plot this under the other function. You see voltage U over phase angle phi U, and we have here the intersection, here the maximum, and we will have a function that looks like this, with the same amplitude as up here, the maximum, the absolute of U, and we have here now not time values, but phase angles. We begin by 0 degrees. If we recall, point number 1 here is at a phase angle of 0 degrees. It's on the x-axis. And if we go towards point number 2 in this case, the phase angle that we have here, phi u, it's rising. And it's rising here towards 90 degrees at its peak, crossing the zero at 180 degrees when we've moved all the way over here, and we have completed half a circle, 180 degrees, and we're back on the x-axis, just negative. And we complete this endeavor through 270 degrees and back to 360 degrees. What we've achieved now is we've described this time-dependent function in terms of phase angles. And phase angles in this case, they stay. They're more easy to describe because the speed with which the function may move through time varies, but it always moves through 360 degrees. Now, we have considered not just one sinusoidal function, but we have also considered the current response, for example, of a system that we apply such a sinusoidal voltage to. What this means is we will often try to describe the relations between different sinusoidal functions. Now, these sinusoidal functions don't always start at the same phase angle. Oftentimes they move through time with the same amount of degrees per given period, but they will have different amplitudes and they will be shifted. This is what we will commonly experience. Now let us consider how such a shifted sinusoid would be described in this circular coordinate system here. Let me draw a current response for a capacitor into this diagram. For the capacitor, as we have discussed last time, the current has its maximum where the rate of the rising voltage is the highest, and this kind of function. Well, essentially we again obtain a sinusoid, but it is shifted by 90 degrees. We have here the amplitude I. For consistency, I will call the maximum of u the absolute of u. And now let us think about where this function is when we consider again these same points in time that we have considered for the voltage. Let's begin by point number 1. We are not starting where this function is on the x-axis because the function is obviously at its maximum. And the function immediately begins to fall off. So on this circle, where the function is at its maximum over here and begins to fall off, this corresponds to this point. So we are here. If we draw this over here, we end up at this point. Note that we end up at a point that is a different distance away from the origin than the points on the voltage function, because the current here, as I've drawn it, is not as high. The amplitude is different, so the radius of the circle also will turn out to be different. And we start with point number 1 here, instead of here. And as we move towards point number 2, we have fallen off slightly. We reach point number 2 here. And on it goes. We cross at point number 3, the x-axis, where the magnitude of this function is 0. We cross the 0 point. And we continue on this circle. We hit point number 4. At point number 4, this is just before the negative maximum of the current. We are here. If we project this over here again, find this point and move over here. And then we move through point number 5 and arrive at the origin, as we have just extensively discussed. And this way, we again complete the circle. We complete it in the same direction, mathematically positive direction. But what has changed is that we do not start at the same phase angle. The phase angle for the current I will now call consistently phi I. And I will draw it again for the point number 2, where I have drawn here the phase angle for the voltage. You see that at the same point in time, point number 2, the phase angle of the current is considerably larger already than the phase angle of the voltage. If we move through this function and move through time and increase the time, what happens is that these points move with the same speed along these circles, but the current is always 90 degrees ahead, or has a phase angle that is 90 degrees larger than the voltage. I will draw this just for explanation's sake for a different point, for example for point 4. So this becomes more clear. For point 4, we are over here. We have projected this current at this point here. And for the voltage, where we end up is here, just before it intersects 0. So we find this point here. What you will discover is that the angle between these two points that are moving along this circle always stays constant, and it's always 90 degrees. And what also stays constant, because it's the same wherever you are on the circle, is the radius of the circle. And these are essentially the two parameters that you need to describe the relation between these functions. If we plot the current in an analogous display to the voltage over phase angle description here, we can do essentially the similar thing, except that our phase angle for the phi I starts not at 0, but at 90 degrees. I will add the phi I to the axis. It's written in red. So we start here, slightly lower, have a different amplitude. And we start here at 90 degrees. And then we move to 180 degrees, 270 degrees, 360 degrees. And when the voltage has completed one complete period, we are again at 90 degrees where we started. So the speed at which the phase angle changes is the same, but the distance is there. Now, how do we describe this relation between the voltage and the current? The convenient way that we have chosen so far is to just divide them by each other. Now let's think about what this means in this kind of description here, in this coordinate system with the moving circles. So it doesn't become too confused, I will just draw this exact same coordinate system again, just below here. We have our voltage circle again, and we have our current circle. And I will pick 2 points along the circle. For example, again, point 2, where the voltage is here, just above the 0 line, where it's just started rising. And the current is correspondingly over here, point 2. Now, if we divide them by each other, what we obtain is some point here. Now first, what is the distance of this point from the origin? The distance of this point from the origin is just the length of these vectors here, so the absolute, or the magnitude, the amplitude of the voltage, divided by the amplitude of the current. And in this case, because the voltage is slightly larger than the current, so it's reduced somewhat. So perhaps, depending on the concrete values, it turns out to be in this distance here. So somewhere on this circle there is a point where the impedance lies. Now, where is it? Where's the impedance? The impedance also must contain the information by which angle the current and the voltage are shifted against each other. And in this case, it's 90 degrees. And it's positive 90 degrees because the current is 90 degrees further ahead than the voltage. So, let's plot it here. And what we achieve is a description for the impedance. And note now that this point, with its magnitude absolute of z and its phase angle phi z. I will write this again larger here. Phi z is the phase angle of the impedance, and the absolute of z, which we sometimes also name r, is the magnitude of the impedance. They do not change now. The phase angle of this impedance stays the same, precisely because the angular difference, the angle between voltage and current, always stays the same. So these phase angles of voltage and current, they move, but the phase angle of the impedance doesn't. And what we have achieved now is basically we found one point in this coordinate system which displays our sinusoidal functions, which stays constant in this entire enterprise. And so with this phi z and the absolute of the impedance z, or r, we can now describe the relation between voltage and current. This is now our description that we can handle, which tells us how our system basically responds to this voltage that we apply. Alright, now that we've talked about how to represent our sinusoidal functions and interpret them in different ways, in this case as a point rotating on a circle, let us think about how to mathematically describe such a function, perhaps even in a more convenient way, so that the calculations get easier. In the time domain, we can represent this generalized sinusoidal function, for example, like this. U as a function of t is an amplitude, the absolute of u, times either sine or cosine. In this case, I will choose for convenience the cosine of the phase angle, and the phase angle in this case is time dependent, the angular frequency times time, plus the initial phase that it starts with. And this describes, in the general case, our voltage waveform that we apply to our system. We can formulate the current response in a similar way. We have our amplitude, the absolute of I, times the cosine of omega t plus phi I initial. Now, we have considered that we can interpret these kinds of functions as a point rotating on a circle. How can we mathematically and conveniently describe such a system? And as it turns out, we can describe it using complex numbers as a helpful tool. I will now briefly recapitulate the basics of complex numbers and the forms that we can use them in to show how they relate to this type of analogy. Before, I had generalized this rotation of the point in an xy coordinate system. In the complex, for complex numbers, we are using the complex plane, and it consists of the imaginary axis and the real axis. I will denote the imaginary axis with IM for imaginary, and the real axis with RE for the real axis. And in this complex number plane, all complex numbers are located. And now let's consider how we describe where such a complex number is. If we place it here, z, this is the lowercase z, and I use an underscore to denote that it's a complex number. So how can we describe where this complex number is located? The first way is very familiar because it's the same way we've described how this point moves here. And it is with a distance from the origin which is the magnitude of the complex number, and with a phase angle, under which it is with regards to the real axis. And in complex numbers, we can write them, if they have this form, with the following equation. They are the magnitude of the complex number, the length of this vector, times e to the j denotes the imaginary unit, times the phase angle under which it stands, phi z, in this case z as an index for the complex number. It can be shown mathematically that this e to the j phi z term can be expressed with trigonometric functions. And it is, in this case, the cosine of phi z plus j times the sine of phi z. If we plug this into this equation here, we get the following result. The amplitude stands. And we can also multiply these terms out so that we have z, the magnitude, times cosine of phi z, and we multiply this out, this magnitude, with a sine of phi z times j, and then we receive magnitude here times cosine of phi z plus the imaginary unit, scat, times the magnitude of z times sine phi z. And as you see, with the exception of this imaginary unit here, everything else boils down to some number. The cosine and the sine will be some value varying between 1 and minus 1. And this length of the vector is also just a number we can express. And so we can contract this magnitude of z times cosine of phi z to some number. And this term here, the magnitude of z times sinus of phi z. And we call this, in this case, the real part of the imaginary number. Again denoted as Re of z. And we call this term here the imaginary part of the complex number. The j over here, contract the imaginary part, and we receive this form. Now, what do these forms mean in terms of showing us where the complex number is in the complex number plane? Let's begin with the last one that we just derived. The real part is just the coordinate here on this axis, and the imaginary part is just the coordinate here on this axis. This is in z, and this is now re z. Slightly more complicated is the relation with the trigonometric functions. Briefly recall how these trigonometric functions are defined. I will draw again this coordinate system here, where we have the imaginary axis and the real axis. And now consider that we have here a complex number z in a distance absolute, the magnitude of z from the origin, and under some angle phi z. And if we find the coordinate, the real part of z down here, this forms a triangle with a right angle down here. And here we are at the real part of z. And what this means is that, for example, the cosine of phi z is this side of the triangle divided by the magnitude, the longest side, the hypotenuse of the triangle. And this is how these values relate. This calculation can be performed analogously for the sinus. Now, with this mathematical background in mind, let us move to how we can apply this kind of representation to our voltage and current waveforms. Let us apply it first to the complex voltage. Let us begin with this kind of representation. We already derived why it can be described as a point rotating on this circle. And so now we just use this display of this kind of rotating point, but with a complex number. And so we have the complex voltage U with the underscore to denote that it's a complex number. Yeah, it's this one. Equals the magnitude of the voltage, which we have previously used in our equation, except this time we name it as the magnitude of the complex number. And we also know what the phase angle is, because the phase angle is the argument of the cosine. And the argument of the cosine here is known, it's phi u. Similarly, the argument of the current function is known, this is phi I. Note the difference, this phi I initial and the phi u initial are the offsets, the initial offsets, and the phi I and the phi u, the larger terms, are time dependent. And now, if we plug this into this form, we have some phase angle, and we represent this as a to the j phi u, and phi u we know here to be omega times t plus phi u initial. We can write this in completely analogous form for the complex current. We have our amplitude times this way of displaying it, e to the j omega t plus phi I initial. Now we have a different mathematical way of expressing our voltage and current. What we have discussed before is that we want to understand and mathematically describe how our electrochemical system responds to, for example, such a voltage excitation. And for this we want to know the relation between voltage and current. And for this, we divide the complex voltage by the complex current to arrive at the impedance. And this impedance we call capital letter Z. Now, Z, we define ourselves as the relation between voltage and current in the complex representation. And so we use the complex voltage and divide it by the complex current. If we do this, and we use these representations, then we will get a term that begins with the quotient of the magnitudes of the voltage and the current. And note that while this may look somewhat interestingly denoted, it is basically just the number. This will be some amplitude, and it's mathematically simple to handle. And the second part of this impedance is the division of these exponential terms now. If we divide exponential terms, what we will get out is an exponential term where the exponents are subtracted. So this exponent will be subtracted from this exponent. Let me write this out. We'll get some term e to the j times omega t from the voltage plus phi u initial from the voltage. And since we divide it by the complex current, what we will have is subtraction of omega t minus phi I initial. And what is most remarkable about this omega t and this omega t, they cancel out. And these two terms are the only time-dependent terms here. So what we receive is some magnitude times e to the j, some constant phase angle, which means that our impedance is not time dependent. We have now found the constant relation between the complex voltage and the complex current. And this we will call the magnitude of the impedance, Z. And this phase angle we will call phi Z. And with this, we have arrived at an initial mathematical description of our impedance as the quotient of the complex voltage divided by the complex current. Now let's look at different forms, how we can write the impedance Z, as we've just looked at the complex number representations. We can transform this into the cosine of phi Z plus j sinus phi Z representation. And if we now find the real and the imaginary part of the impedance, then we can again contract Z, the magnitude times cosine Z, plus j, the magnitude times sinus phi Z, and what we end up with is something that looks like this. The real part of the impedance plus j times the imaginary part of the impedance, which are again related by sinus phi Z and cosine phi Z to the magnitude. And for the impedance, we give these real and imaginary parts specific names. And the real part we are calling resistance. So the resistance of impedance, it's not quite the same thing as the one-dimensional resistance that you find with an ohmic resistor, because it's a part of a two-dimensional number. It is the resistance part. Resistance of the impedance plus j times x, and x we call the reactance of the impedance, which is the imaginary part of the impedance. And if we again apply our perspective on what these mean in the complex plane, let me briefly draw the complex plane once more with the imaginary axis and the real axis. This impedance is located somewhere in this complex plane, because it is now a complex number, and it is located where the real part is R. This is the real part, and where the imaginary part is the X. Let's make it here. And where these two intersect, our complex impedance is located. And this relates to this kind of display, as we've discussed now multiple times, with this distance from the coordinate origin, where we have the magnitude of the impedance and the phase angle phi Z, under which it is to the real axis. And again, if we try to calculate the real part, this relates with a cosine to the magnitude. And these are the ways that we can mathematically formulate the impedance as the complex quotient between the voltage and current.